The effects of cold and desiccation. This is also one of your learning targets. The principal benefit of cold treatment is to slow growth of cultures and microbes in food during processing and storage. Cold merely retards the activity of most microbes, so basically it puts them in a dormant state. Most microbes are not adversely affected by gradual cooling, long-term refrigeration, or deep freezing. Very, very low temperatures, like -degrees Celsius, can preserve cultures of bacteria, viruses, and fungi for long periods. Why is this important? Well, if you can control when your microorganisms grow and you can keep them for long periods of time in a freezer, it's very beneficial for research. If you can come out and say, okay, I need to work with this bacteria today, you can pull it out of the freezer and you can grow it on a plate, and then you can do your experiments. So it's really very beneficial in being able to understand how microorganisms work and in research. So desiccation and lyophilization. Desiccation is basically dehydration, removing the water from the microbes. Some microbes are killed by desiccations, and some others it doesn't have any effect. Lyophilization is basically desiccation and freezing. So you're removing the water, you're turning the microorganism into a powder basically, and then you're putting it in the freezer so that you can use it later. Radiation. It's energy emitted from atomic activities and dispersed at high velocity through matter or space. This is one of your learning targets. So gamma rays and X-rays are ionizing, and ultraviolet radiation is non-ionizing. So ionizing radiation is an alternative method to sterilizing materials sensitive to heat or chemicals. Non-ionizing radiation must be in direct contact, so it has to be able to contact the surface of whatever it's trying to control. And it's useful against fungal cells and spores, bacterial, vegetative cells, protozoa, and viruses. Filtration. This is a physical method of controlling microorganisms. It's an effective method to remove microbes from the air and liquids. Its fluid is strained through a filter with openings large enough for the fluid to pass but too small for microbes. Pore size can be controlled to permit true sterilization by trapping viruses or large proteins. Remember, there's a size chart on what size proteins and viruses and bacteria and all. So they can determine a pore size based on that. Used to prepare liquids that cannot withstand heat, such as serum, blood, products, vaccines, drugs, IV fluids, enzymes, and media. Basically, things that have proteins in it. You cannot use heat or you'll denaturize the proteins in what you're trying to keep clean. It's a very important step in water purification. So it's unable to remove soluble molecules like toxins that can cause disease. And it's a highly effective particulate filters. They're used in hospital rooms and sterile rooms. You've heard of HEPA filters. Osmotic pressure. This is adding large amounts of salt or sugar to foods to create a hypertonic environment for bacteria, causing plasmolysis. Plasmolysis is just a fancy way of removing water from the cell. Pickling, smoking, and drying foods have been used for centuries to preserve foods. Osmotic pressure is never a sterilizing technique. So basically, you're drawing the water out, trying to draw the bacteria out. You're giving the bacteria and other microorganisms less of what they need to grow. Chemical agents and microbial controls. They occur in liquid, gaseous, and solid states. They range from disinfectants and antiseptics to sterilants and preservatives. An aqueous solution is something that's dissolved in water, and tinctures are chemicals that are dissolved in pure alcohol or a water-alcohol mixture. Selecting microbial chemicals. This goes along with the desirable characteristics of chemical control agents in your learning target. rapid action even in low concentrations. They must be soluble in water or alcohol, and they have to have long-term stability. They need to be broad spectrum action without being toxic to human and animal tissues. Penetration of inanimate surfaces to sustain a cumulative or persistent action. Basically, they can't disappear and then not be helpful anymore. They need to be resistant to becoming inactivated by organic matter. So basically, when they touch tissue, they can't become inactive. They need to be able to still work. Continuing on, they're non-corrosive or non-staining properties. They sanitize and deodorize properties. They're affordable and they're very easily to find. So no chemical can completely fulfill all of these requirements, but glutaraldehyde and hydrogen peroxide approach this, are the ones that closely approach this. So let's talk about chlorine. You guys know chlorine is bleach. You know it's used in swimming pools. It can kill endospores, all other microbes, and it can be in a liquid or gas form. It denatures enzymes and suspends metabolic activities. It disinfects drinking water, treats wounds, disinfects bedding and instruments. It sanitizes food equipment in restaurants. It's less effective exposed to light, alkaline pH, and excessive organic matter. This is one of your learning targets. Iodine, also one of your learning targets. It can kill endospores and all other microbes. It's found in liquid form. It interferes with metabolic process or metabolic function. It's a topical antiseptic. It's a disinfectant for plastic and rubber instruments. They use iodine when you give blood. They'll put it on the skin where they're going to insert the needle when they do blood donations. And it can be extremely irritating in the skin and toxic when absorbed. Phenol. Phenol kills some bacteria, viruses, and fungi. In high concentrations, they are cellular poisons. They disrupt the cell wall and membranes and proteins. In lower concentrations, they're inactivated. They inactivate certain critical enzyme systems. The toxicity of many phenolics make them dangerous to use as antiseptics. They're used in drains, cesspools, and animal quarters. Chlorhexidine kills most bacteria, viruses, and fungi. They target both bacterial membranes where selectively permeable is lost and proteins resulting in denaturization. So they go for protein denaturization. They're used in hand scrubs, prepping skin for surgery. They can be in some mouthwashes. They may not be as effective on some viruses and some fungi. Hydrogen peroxide. It kills endospores and all other microbes. It's found in a liquid form. It's used for skin and wound cleansing, mouthwash, and bed sore care. It's a sporocidal only in high concentrations. So when we use it, I try to get at least 10%. And when it's 10% hydrogen peroxide, it's very dangerous to the human tissue. Once again, learning targets. All of these are learning targets at this point. Heavy metal control agents. They kill some bacteria, viruses, and fungi. They can be in an ointment or liquid form. Mercury, silver, and other metals exert microbial effects by binding onto functional groups of proteins and inactivating them. Organic mercuril serve as preservatives in cosmetics, ophthalmic solutions, and other substances. They are not effective against endospores, and they can be toxic if inhaled, ingested, or absorbed. Aldehyde agents. They kill endospores and all other microbes. Glutaraldehyde disrupts the activity of enzymes and other proteins. It's somewhat unstable, especially with increased pH and temperature. Formaldehyde attaches to nucleic acids and functional amino acids, so it's going for protein denaturation. but it can be extremely toxic and irritating to skin and mucous membranes. Ethylene oxide. This is a gas. It takes 2 to 4 minutes to kill Streptococcus facilis, and it can take up to 25 hours to kill a flu virus. It is used in small quantities. Other antimicrobial agents and dyes are dyes, acids, and alkalis. Dyes are active against gram-positive bacteria and fungi. They're limited application because they stain and have a narrow spectrum of activity, so they have a very specific niche. Acids and alkalis, they're very low or very high pH, can destroy or inhibit microbial cells. They're limited in applications due to their corrosive, caustic, and hazardous nature. Ammonium hydroxide is used in detergents, cleaners, and deodorizers, and organic acids are used in food preservation. Factors affecting the germicidal activity of chemicals. So the nature of the microorganism being treated, the nature of the material being treated, the degree of contamination, the time of exposure, strength and chemical action of the germicide. All of these factors play a role in how active a germicidal will be.